Let's take on some previous year gate problems from fluid machinery. So the first question is, at the inlet of an axial impulse turbine rotor, the blade linear speed is 25 meter per second. That is u is equal to 25 meter per second. I'm going to use the notations that we generally use. Okay, so it is denoted by u. The magnitude of absolute velocity is 100 meter per second and the angle between them is 25 degree as shown in the velocity triangles. These are the velocity triangles which have been given to us. One is the inlet velocity triangle and the other is the outlet velocity triangle. The relative velocity and axial component of velocity remain the same. This is the key line, that the relative velocity and the axial component of velocity remain the same between the inlet and outlet of the blades. The blade inlet and outlet velocity triangles are shown. Assuming no losses, the specific work in joule per kilogram is, okay, take care of the units in joule per kilogram. Okay, so from this velocity triangle and the data which have been given to us, the magnitude of velocity, absolute velocity, is 100 meter per second. So this becomes v1. Okay, and this becomes 78 meter per second becomes vr1, that is the relative velocity at the inlet, and it's given that the relative velocity remains the same, so this becomes vr2, that is the relative velocity at the outlet of the blade, and similarly this becomes v2, that is the absolute velocity at the outlet of the blade. Okay, 25 meter per second is what? This is u, the blade linear speed, 25 degree, and the angle between the absolute velocity and the blade linear speed is 25 degree, that is also given to us. So can I say this component, this vertical component is vf2. Similarly here the vertical component is vf1. Okay, what will be, okay, we have to find the specific work. The specific work is equal to vw1 plus vw2 into u. What is vw1? Vw1 is the whirl component at inlet and vw2 is the whirl component at the outlet. So this is the formula for specific work. So u is given to us, that is 25 meter per second. What you have to find? vw1 and vw2. Okay, so in this velocity triangle, tell me what will be v1, or I mean vw1, sorry. So vw1 will be the horizontal component of v1, okay, up to this portion. So this will be vw1. Okay, similarly vw2 will be the horizontal component of the absolute velocity at outlet, that is v2, and v2 is this. So the horizontal component will be this. So this is vw2. Okay, so now we have to find vw1 and vw2 and we'll get our answer. So now I guess this is the trigonometry portion. We can find vf1. Vf1 is equal to, I guess it is, yeah, 100 sine 25 degree. Okay, from this triangle a b c. Okay, so this will be 100 sine 25 degrees. Solve it. This will be 42.26 meter per second, and this will be equal to vf2 because it has been given that the axial component of velocity also remain the same. Okay, so this will be vf2. So now vw1 will be v1 cos 25 degree from the same triangle, so that will be 100 cos 25 degree, which is 90.63 meter per second. So now we have got vw1. Okay, let's move on to vw2. How can we find vw2? We know vf2, great. So if I know this theta, okay, I can know vw2. Can I find this theta? Yes, because hypotenuse is given perpendicular, we know that. So sine theta becomes vf2 upon 58.6 meter per second is given. Solve it, you will get theta is equal to 46.15 degrees. Okay, so vw2, that implies vw2 will be equal to 58.6 cos of 46.15 degrees. Okay, basic trigonometry. So this will be 40.59 meter per second. Now we have VW1 and VW2 and U also. So put all these values in equation 1 and you will get your answer. So specific work is equal to VW1 plus VW2 to U, which is equal to, put the values, you will get the answer as 3280.5 joule per kg. Okay, take care of the units. Before filling the answer here, always check the units in which you have been asked the answer. Okay, so answer will be 3280.5. okay, so next question. So Kaplan water turbine is commonly used when the flow through its runner is, okay, you know that the Kaplan turbine is an axial flow turbine used for low head and high discharge. So according to the options, the answer will be B, axial, and the head available is less than 10 meters. Okay. Some additional information that I would like to give, that for Pelton turbine, there is generally high head, like above 200 meters. For Francis turbine, medium head is used, 30 meters to 200 meters, and whereas for Kaplan turbine, the head is less, that is around less than 30 meters. Okay, so next question. Consider two hydraulic turbines having identical specific speeds and effective head at the inlet. Okay, so we have two hydraulic turbines that have identical specific speed and identical effective head at the inlet. The speed ratio N1 by N2 of the two turbines is 2. The respective power ratio is, okay. So pretty simple question. You know the formula of specific speed, that is N root P by H raised to power 5 by 4. Okay, so this is the formula for the specific speed. Now equate ns1 is equal to ns2. Okay, so that will be N1 P1 root P1 upon H raised to power 5 by 4 is equal to N2 root P2 H raised to the power 5 by 4. Head is same, so this gets cancelled out. This gets reduced to N1 root P1 is equal to N2 root P2. Okay, N1 by N2 is given, you can find P1 by P2, like N1 by N2 is equal to under root of P2 by P1. Solve it. P1 by P2 will be equal to 0.25. So the answer will be 0.25. Okay. Next question. Okay, so the blade and fluid velocities for an axial turbine are as shown in the figure. The magnitude of absolute velocity at entry is 300 meter per second at an angle of 65 degree to the axial direction. Okay, absolute velocity at entry is 300 meter per second, angle is 65 degree to the axial direction, while the magnitude of the absolute velocity at exit is 150 meter per second. Okay, absolute velocity at exit is 150 meter per second. The exit velocity vector has a component in the downward direction, given that the axial velocity is the same. Okay, the axial velocity, that is the horizontal velocity, is the same at entry and exit. We have to find the specific work, but this time the units in which you have to put the answer is kilojoule per kilogram. Okay, so let's take the components of the velocity at inlet, that is 300 meter per second. This is 65 degrees, so this will be 300 cos 65 degree, and this will be 300 sin 65 degree. Okay, this becomes the axial component. Okay, and at exit this is 150 meter per second. The angle is not given, however I can say that the axial component for the exit velocity will also be 300 cos 65 degree, because it is given that the axial velocity is the same at entry and exit. So if we know these two components, I can find out theta. Okay, so first of all, let's see what is 300 sine 65. This is 271.89 meter per second, and 300 cos 65 will be 126.785 meter per second. Okay, so these vertical components, what are they? They are actually whirl components. So this becomes VW1, that is whirl component, whirl velocity at inlet, and this component becomes VW2, that is the whirl component of velocity at outlet. Okay, so now I have the values. 300 cos 65 is equal to 126.785 meter per second. Can I find cos theta? Yes, cos theta will be 126.785 upon 150. So this theta will be 32.303 degrees. Okay, so this will be 32.303 degrees. Great. Now VW2 becomes 150 sine 32.303 degree. Okay, and the value of this component will be 80.159 meter per second. What we have been asked, specific work in kilojoule per kilogram. Okay, so this will be VW1 plus VW2 into you. Same repeated question. I mean, they even haven't changed the concept. 271.89, same formula is there, plus 80.159, sorry. U, what is U? Blade speed is given 150 meter per second. Solve it, the answer will be 52807.7. This will be in joule per kilogram, so that will be 52.807 kilojoule per kilogram. So answer will be 52.807 kilojoule per kilogram. Okay, so let's move on to the next question. Which one of the following is not a rotating machine? Okay, let's check the options. Centrifugal pump, it has rotating impeller and vanes, so this is not the option. Gear pump, it uses meshed gear to pump fluid, so gear rotates, this option also gets rejected. Jet pump, is actually based on ejector principle with nozzle and diffuser, and so this is without any rotary parts, so C, jet pump is the answer. About vane pump, it consists of vanes mounted on a rotor that rotate inside a cavity, so this is also a rotating machine. And according to the question, which one of the following is not a rotating machine? So jet pump is the answer. Which one of the following statements is true? Okay, both Pelton and Francis turbines are impulse turbines. Okay, so you have been asked that which is the impulse turbine, which is the reaction turbine. Okay, so Pelton is actually impulse turbine. Let me write here. Pelton turbine is impulse turbine. Okay, Francis is actually radially inward and axially outward. Okay, so the flow that exits is in axial direction and axial out. Okay, and whereas Kaplan is axial in and axial out, so this becomes a pure reaction turbine, axial out. Let's check the options, and according to options, D will be the answer. Kaplan turbine is an axial flow reaction turbine. Pretty simple question. Okay, I guess this same type of question has been asked in this year's GATE also, GATE 2019. The question based on similar concept, I guess, I mean similar theory. So next question, right here, GATE 2019 also. So you see the questions get repeated in GATE every year. Okay, for a Pelton wheel with a given water jet velocity, maximum output power from the Pelton wheel is obtained when the ratio of the bucket speed to the water jet speed is 0.5. We do remember this, uh, what can I say, relation, that for maximum power output U is equal to V1 by 2. Okay, so U by V1, that is the ratio of bucket speed to the water jet speed, will be 0.5. Pretty simple question. Okay, a test is conducted on 1/5 scale model. So 1/5 scale model, this is a data model of a Francis turbine of head 2 meters, volumetric flow rate 1 meter cube per second at 450 rpm. Take the water density and acceleration due to gravity as 10 raised to the power 3 kilogram per meter cube and 10 meter per second square respectively. Assuming no losses both in model and prototype turbines, the power in megawatt of a full-sized turbine while working under a head of 30 meters. Okay, so let's find out the power of the model turbine first of all from the given data. So power of model turbine, that will be rho g q hm. Okay, the usual notation that we use: density, this is acceleration due to gravity, this is volumetric flow rate, this is effective head. Okay, so this will be 10 to the power 3 into 10 into q. Q is flow rate, that is 1 meter cube per second, into head 2 meters. For model, the head used is 2 meters, so this will be 20 kilowatt. Okay, so this will be 20 kilowatt. Now for these type of questions we use three relations which you must know, that is D is directly proportional to root h and inversely proportional to n. This is speed in rpm, this is effective head, and D is diameter. Okay, volume flow rate has a relation with head and speed. Similarly, power also has a relation with head and speed. So we use these three equations to, relate the model turbine and the prototype turbine. Okay, so we have to find the power while working under a head of 30 meters, power of a full-sized turbine. Okay, 1/5 scale model is given, so that is we have been given the relation between the diameter of the model turbine and the diameter of the prototype turbine. Okay, so we can use this equation 1 and this equation 2 to get our desired result. How? I will replace n from this equation, like n will be directly proportional to root h by d, and I will put this in equation 2 so that I will get the final relation in power and head and diameter. Okay, why I have done this? Because we have been given a relationship between the diameters of both the turbine and we know the effective head of both the turbines. So putting these values, I'll get the power of the prototype turbine. Okay, so let's begin. So power will be h raised to the power 5 by 2 upon n square. This is n, be careful. So this will be h upon d square. I take d above, so this final relation will be h raised to the power 3 by 2 into d square. Okay, so that implies p is equal to, let k be any constant, h raised to the power 3 by 2 d square. Okay, so for model this will be k hm 3 by 2 dm square. I am directly dividing it, so this will be for prototype. Okay, k gets cancelled out. So now d model by d prototype is 1 by 5. 1/5 scale model is given. Okay, and we know the heads of both the turbines, that is the model turbine and the prototype turbine. So put the values. The power of model turbine is 20 kilowatt, that is 20 into 10 to the power 3 watt. Power of prototype turbine is denoted by pp. hm, that is 2 raised to the power 3 by 2 upon 15 raised to the power 3 by 2 into 1 by 25. Okay, from here solve this, you will get the power of prototype turbine as 29.047 megawatt. Okay, be careful that you have to fill the answer in megawatt, so this will be 29.047 megawatt. Okay, always use these three equations to solve these type of questions. I mean, here in this question we have used equation 1 and 2 to get to our desired result. Maybe in some other equation we can use 1 and 3 equation to get to our desired result. It depends on the data which has been given in the question. So thank you.